Okay, so today we are continuing with limits, but now we're going to jump into limits and trigonometry. So we're talking sine, cosine, tangent, and etc. All the fun stuff and how limits are going to apply to those. While you are writing this down and thinking about the pun that is shown, which actually was a lot funnier before the allegations over the last couple of years, so maybe I shouldn't use this one anymore. But you should know and remember a little bit about trig in terms of, what is tangent, and it's sine over cosine, or how do you reduce a quotient like this, how can you simplify it? So we're going to have to do a little bit of remembering some identities, but it's not bad. I promise it's not bad. And you do need your unit circle. So if you don't have unit circle memorized, memorize it, number one, but for the sake of right now and today, if you have a copy of your unit circle and you want to get that out as a quick reference while we're going through the notes, then please do so now. All right. So we are going to start with just a good old-fashioned limit where you see trig instead of just a polynomial or a quadratic or a rational or something like that. So how do you evaluate a limit if it's something like sine? Well, it's going to be possible with sine and cosine a lot of times through direct substitution because the graphs of sine and cosine are continuous, okay? So right off the bat, sine and cosine are continuous, and since they are continuous, a y value exists everywhere, therefore a limit exists at a specific point, okay? So all you're going to do is plug it in, right? So what is the sine of pi over 3? Well, if you think about your circle, that would be the y value at 60 degrees, let's say, and that should just be square root of 3 over 2. So it's just like what you did before, you just have to know your unit circle, okay? What about the cosine of 5 pi over 6? So remember, that's in quadrant 2, right? So it's over here somewhere. And cosine means the x value, right? So the x value of pi over 6 is going to be negative because it's in the second quadrant, and it's going to match the x value that was over there, okay, which is the square root of 3 over 2 again, okay? And then what about something like this? Well, if you multiply sine and cosine, it's not going to create something, that's discontinuous. It might be a funky graph, but it's still going to exist everywhere. So you can test by just plugging in pi and seeing what happens, right? So the cosine of pi would be over here. The x value over there would be -1. The sine of pi would be 0, and then you'd add that 2 on to the back. So your answer here would just be a 2. So if you can plug in and you get a real number answer, you're good to go. So you might want to make a side note of that. Always try plugging in first. And if you get a real answer, you're good to go, right? If you get a real number answer, good to go. Real number answer, Elfine. Okay, you are done. You are finished. It is the answer. Okay, so let's talk about some areas then where maybe it doesn't work out so nicely, or maybe areas where you know that it's going to be discontinuous. Okay, so here are the two things that I thought about for causing a problem. Discontinuities are huge. They're going to cause a problem. And what kinds of discontinuities have you learned about? Well, you've learned about vertical asymptotes and maybe even holes, right? So, or gaps in the graph. So all of those are discontinuities where you need to be careful, and maybe the limit will or won't exist, right? You've got to think about it. So let's write a couple of examples of something that's going to have an asymptote. So let's just do something like the graph of tangent. You might remember the graph of tangent. If you don't remember it well, it looked something like this. Whee! And the asymptotes on this were at pi over 2, in increments of pi over 2 plus pi. So if you are given the graph of tangent and they straight up are telling you to look where there's an asymptote, then you've got to be super careful because it is not going to exist if there's an asymptote there, okay? And so another graph that you might need to be careful of is something like, let's say cosine of x over sine of x as x approaches 0, okay? If you are given this, what's going to happen here is you might try direct substitution first, and you're going to have a denominator that's 0, so kind of like these examples that are going to be in a second. But you also might remember that cosine over sine is the same thing as cotangent. And so if you know the graph of cotangent, then there is a vertical asymptote at 0. So you would automatically know that this was a does not exist. So just kind of be careful with that. And then down here, maybe a denominator that will be 0. This one kind of is the same thing as what's above, but maybe it's something like the following. Okay, so if it is something like this, cosine of x over x, and you try to evaluate and you plug in your 0, you are going to get a 1 over a 0 whenever you do direct substitution. And a 1 over a 0 means that it's also going to be a does not exist. Remember, if it's 0 over 0, you have to be careful, okay? So if you don't have that in your memory bank somewhere, be careful on 0 over 0. But if it's a number over 0, it's going to be does not exist, okay? So maybe like one other example of something like that. Maybe it's like the limit of, I don't know. It's like 1 plus x squared over the sine of x as x approaches pi, something like that. Okay, so here's another random problem. It's got trig mixed in with other stuff. So if you try to plug in the pi, then you're going to end up with 1 plus pi squared all over the sine of pi. Well, what's the sine of pi? Well, that's just a 0. So once again, you have a number over 0, which means that graphically there is probably an asymptote happening, and it's a does not exist. So all of those are like, just be super careful. Try to plug it in. If it's a number over 0, you can say does not exist, okay? But along that same note, be careful, okay? Be careful, guys, because you might think that it's a does not exist, okay? But it really will have an answer. It really will exist. And that's going to go along with what I was just saying, that whole 0 over 0 situation. You have to be super careful. And for the y, okay, I want you to think about the fact that 0 over 0 is undeterminable. And a lot of times, if it's undeterminable, then that means something funky is going on that you really could figure out, okay? And this is where a new theorem is going to come about. Yay! So you should have already learned about the intermediate value theorem. This is the second big theorem. It is called the squeeze theorem. And so I'm going to let you write this down, and then I'm going to explain how the picture actually justifies what you see over here, okay? So hit pause, take a second, write it down, and then we'll talk about it. Let me zoom in a little bit on that, actually. It's kind of hard to read. There we go. Okay, so a lot of people have a hard time understanding just reading this theorem, but I promise it's really easy, and it's actually almost like a cousin to the intermediate value theorem. What this is saying is, use your picture to make this make sense. If h is less than f is less than g. So in other words, look on the y-axis and look at where these are located. Okay, notice how h is the least value function, right? It's the lowest function on the graph. F is the next highest, and G is the greatest function listed. So that's kind of what that's saying. So if this is happening, and then you know that the limit of the bottom function as you're approaching a specific value, if it has a specific number limit, and that is equal to wherever the top graph is also heading, then it's going to force the one that's in the middle to also have the same limit. I mean, like, you can see the squeeze happening right here. So the limit of h is, let's say that's the number 3, okay? So the limit of h as x approaches c is 3. The limit of g as x approaches c is also 3, well then that f that's trapped between them is forced to also be the same limit. And this is a very cool theorem that actually two specific trig functions came about that algebraically it was like impossible to figure out. Well, maybe not impossible, there's actually a proof of it, but it's kind of difficult. These two right here, I would memorize these. These are going to show up quite a bit actually. And these are two functions where if I had given you this as a problem, okay, and I said, hey, let's figure this out, and you tried to plug in a 0 up top and a 0 on the bottom, well, you'd end up with 0 over 0, right? And that is undeterminable. And then you would have been like, I don't know what to do because I can't do algebra to factor and cancel, and you probably don't know what the graph looks like. Well, if you want to type in the graph right now and look at it, you would notice that the limit as x is approaching 0 really is 1. It really is attempting to be that 1. And there's a great proof for this in your book. I want to say it's like section 1.3 maybe, or 1 point, I think it's, I don't know, it's somewhere in chapter 1, but there's a great proof if you're interested as to how the squeeze theorem makes this true. So the good news is on that squeeze theorem, you're not going to necessarily have to prove anything with that. I just wanted you to see that so you could see why these two are true, and it has to do with the squeeze theorem, and there were two other functions that forced this to be true. So here's the second one. The limit as x approaches 0 of this right here. Same thing. You would not have known what that looked like graphically, but if you do check out the graph, it's going to be 0. But memorize these two. Once you memorize these two, okay, what's going to happen is you can actually use these two to help you solve some trig functions that you think are or does not exist. So you're going to always look at a problem given, see if it kind of looks like this form, or see if it kind of looks like this form, and if it does, you're going to be able to manipulate it and solve a problem. It's actually kind of cool. So let's look at a couple of examples of that. Try to make some of those up. Yeah, see, look at all those great examples. Okay, it looks like I'm making up my own examples. Okay, so let me show you what I'm talking about. All right, here's just one example. So the limit as x approaches 0 of, let's say, sine of 5x over x. Okay, so let's say that you are given this. And you notice, well, first you would try to plug in the 0, like I said before. Always try to plug that in. But if you do, you're going to get 0 over 0, and you're going to think, I don't know what to do. Well, if you notice that it looks a lot like one of the ones you're supposed to memorize, then you can just kind of manipulate what you see to make this problem work out. Now, be really careful here. A lot of people I talk to, they try to take that 5 and just suck it out. They're like, oh, just get rid of the 5, and then we know that part. And I'm like, oh, just be really careful. The idea is this. If you notice in this equation, it's the sign of something over itself. So, in other words, if the numerator and denominator match and it fits this format, then it turns into a 1. So what you're really supposed to do is you're supposed to tell yourself, okay, the top is 5x, and I really wish that this one and this one would match so that I could use the theorem above. Well, how do you make a 5x match an x? Well, you multiply the bottom by 5, right? If I multiply the bottom by 5, now these match. But it's not legal to multiply the bottom by 5 unless you do the same thing to the top. Okay? And that's legal because now that's just an invisible 1 that doesn't really matter. So by doing this math of multiplying top and bottom by 5, then what you're looking at is the following. Now, these match, right? And this looks just like the equation that was above. And we know that if the limit's approaching 0 of this type of function, the answer's supposed to be a 1. So the limit of this part is really a 1 times the 5 in the front. So the overall limit would be 5. Now, if you didn't like how I justify that algebraically, you're not alone. A lot of people hate when I show the actual math that's happening. A lot of people just say, oh, well, I'm just going to remember that that extra number is just going to make it the answer. And I'm like, okay, that's fine. But I wanted you to see why this was legal to do using properties of limits, okay? So let's do one more example of how you might use something like this. How about the limit as x approaches 0? Of cosine squared x minus 1 over x. Okay, so when you look at this, same thing. You might try to plug in your 0 and you're going to get undeterminable. Okay, now this doesn't look exactly like the one above, but it's got the same components. So you might think, I wonder if I can do anything to kind of make this look like what's above. And the answer is, why, yes, you can. Hopefully you noticed that this is factorable. Okay, and if this factors, this is a difference of squares. So if it's cosine squared x minus 1, you can actually write that as cosine x minus 1 times cosine x plus 1 all over x. So this factors into this, and once you do that, now look at this part. Okay, this part is very similar to what you see above. I realize that the 1 and the cosine have switched places, okay? But that's okay because if you take a negative 1 out of this, like if I factor out a negative 1 from this right here, what am I going to have? I'm going to have negative 1 times, it would be negative cosine x plus 1 over x, and then recopy this. Okay, so now look, I mean, this is great. Now this part is identical to what's above, and you know that's supposed to be a 0, so who cares what all this other crap is? If that's a 0, you're doing negative 1 times 0 times who cares, because 0 times anything is 0. So if you think you can make it look like that theorem above, 9 times out of 10, the answer is going to be 0 if it's looking like the cosine one. And then you just really have to be careful on the other one because you're dealing with a 1, and so other numbers might be possible, just like that 5 that we looked at. Okay, so kind of tricky. You're probably going to want to work with friends on a practice section. But a couple big things out of this were what? Squeeze theorem makes these two things possible. So, you know, if nothing else, I'm like, memorize those two special ones. Memorize two special trig. Know that the squeeze theorem made them possible. Squeeze theorem made them possible. And the third thing is always try direct substitution first. And don't panic unless 0 over 0. Okay. So those are the 3 big things to take away from this video, and good luck to you trying some practice problems.